In this lecture, we take up some more of the GLHEPRO inputs, in this case, the ones related to the borehole design, sometimes called borehole completion. So we're going to talk about, here we go, specification in GLHEPRO and to some degree how the modeling of the borehole design works. This includes the borehole geometry, flow rate, what we call the fluid factor, the borehole filling, grout or groundwater, convection, well, specifically convective resistance inside the tube. There's also convective resistance on the outside of the tube if you have groundwater-filled boreholes. Discuss short circuiting briefly. That's covered in a little more detail in the ground heat exchanger modeling lecture. And geometries other than single U-tube. Actually, we're going to probably give those pretty short shrift, but okay, so the main goals here, providing to introduce specification of the borehole design, modeling of the borehole design, and provide some references for the modeling. So I'm afraid this lecture may be either too much or too little, depending on your perspective. I'm not going to go into detail in the modeling, but I am going to talk about it a little bit more probably than what you would strictly need to know if you were only interested in how to use GLHEPRO. So it's a little bit in between the two. So I apologize in advance. Right, the lecture is not intended to explain the theory or modeling in any kind of detail. And that's one of the reasons for providing all the references. And it's not intended to give complete guidance on how to make a good borehole design, although I will discuss that a little bit. So, another way of looking is what to do with all this. This is the input for the borehole information in GLHEPRO. So we'll partly use this as a way to look at the whole thing. Okay, so the goal here is to look at how the design of the borehole affects the heat pump entering fluid temperatures. Right, that's part of our sizing procedure. So this simulation is affected by and particularly these temperatures are affected by the design of the borehole. If we use thermally enhanced grout, these temperatures won't rise as high as they would with regular grout. That's what we'll be looking at. Okay, limitations of the borehole model. What main thing that comes to mind is that the, say, convective resistance inside the pipe, or if you have groundwater-filled boreholes, the convective resistance outside the pipe, they correspond to a single fluid temperature, or with the groundwater-filled boreholes, also a sort of single operating condition. And this means that if you have a ground heat exchanger where you don't know if the size is going to be constrained by the maximum temperature or the minimum temperature, sometimes we don't know in advance, right, you're going to have to take a guess and choose a fluid temperature that will correspond to whichever design temperature is constraining the design. So if it's the maximum temperature, then you're going to use a fluid temperature around the maximum temperature, and if it's the minimum, then it would be around the minimum temperature, because you'd like to match the resistance to the temperature that's constraining it, the peak that really makes the difference. Yeah, right, and that's why we do this for the design condition. And borehole resistance, it can change significantly between heating and cooling, particularly if in cooling mode the flow drops into laminar flow. So if you have a water antifreeze mixture, usually the viscosity increases as the temperature gets lower. And that can mean in some cases that you drop from turbulent flow into laminar flow and the borehole resistance goes up. So it's something that needs to be considered. Okay, so if we start with the geometry, we have the borehole diameter, what we call the shank spacing, and different people working in the field sometimes define this differently. So sometimes you'll see a shank spacing between the two legs of the U-tube as being the difference, the center to center difference. In our case, it's the wall to wall difference. By pressing these two set buttons, you can choose for the lower one, you can choose the diameters. So in English units, it would be, I think it's SDR11, and I think we have 3/4 inch, 1 inch, 1 1/4, and 1 1/2 inch nominal SDR11 pipe. If you're using Schedule 40 or SDR17, you may have to fix these diameters. And then in SI units, it defaults to there's some standard European pipe sizes, and again, if you may have to adjust it to meet your own situation. And then in terms of the shank spacing, there is, I guess we'll look at this later. I don't think I have an image here for it, but there's some sort of standard spacings that were originally developed by a guy named Neil Paul. He was a graduate student under Chuck Raymond, and he had an A spacing, which was where the pipes were close to touching each other. I think he had an A0 spacing where they were actually touching each other, a B spacing where they were sort of uniform spacing, so the distance from the borehole wall to the edge of the pipe was the same as this shank spacing S, which is the same as the spacing on the other side. So this dimension S and the dimension here from here to here, those were all the same. Okay, so that I guess another assumption or limitation is that we only do this for sort of symmetric spacing, right? We don't have one pipe up against the wall, the other one right in the middle. We recommend the B spacing for uncontrolled placement of the U-tube, so if you're just dropping it down whole, of course it doesn't actually look like this everywhere. And if you have no spacers, well, even if you have spacers, boreholes aren't necessarily straight, so sometimes the pipe may be up against the wall, sometimes it may be in the middle. We found, just based on measuring borehole thermal resistance in thermal response tests, that and doing an analysis like we would do here, the measured or the spacing that typically best represents the actual placement seems to be the B spacing. So it's not up against the wall, it's not in the center. Now, if you use duct tape to tape the two legs of the U-tube together, I recommend against that, then of course you may have a different situation. And there are commercially available spacers, at least I think they're still commercially available, spacers you can put in to, say, more push the tubing up against the wall or closer to the wall. But if you're just dropping it down, again, we found the B spacing to be probably the best estimate. Okay, in here you also specify the volume flow rate per borehole. This is actually computed from the total flow rate and divided by the number of boreholes. So you can change it, but it's computed automatically for the number of boreholes you have and the flow rate you specified. Okay, and the fluid factor, I'm going to come back to that in a couple of slides, so we'll come back to that. Okay, one important thing I'd really like to point out to you, and this is really important if you're a GLHEPRO user, right? There's a critical but unfortunately often overlooked aspect of the design, which we call the hydraulic design. In other words, what's the overall pressure loss of the ground heat exchanger and the system? And I will tell you that many a system design has been ruined by ignoring this. So you can take a system, ground source heat pump system, which is an excellent concept, but if you design the piping and this could be the piping in the boreholes, but also the other piping, if you design it and you put in a bunch of valves to balance the flow, and you have a very high head loss, you can completely ruin the system from an energy standpoint. I mean, if you put a big enough pump in, yes, the system will work, but there are systems that's 30 or 40% of the energy goes to circulating fluid around, and that's just really a bad idea. You can, we'll just say our own analysis shows you can often get under 10% of the total power due to the circulating pump. With the, in other words, 90% plus is used by the heat pump. Kirk Meschers was a really talented design engineer. He passed away. Well, I'm sorry, I've forgotten the year exactly, but I'm thinking it's 3 or 4 years ago now, maybe 2016. But he and I participated in an ASHRAE webinar, and at the webinar, his presentation, he gave as I'll call it design guidance. He didn't like the term rules of thumb. He called them rules of dumb. But for this, I think this is, you could call it a rule of thumb. It's a pretty good one. He said that we should have no more than 25 feet of head loss in the ground heat exchanger, or it would be 7.6 meters, and no more than 50 foot or 15.2 meters total of head loss in the system. I think you can probably do better than that, but as an upper limit, I think it's well worth checking to make sure you're not exceeding this in your system. You can do this by putting too small a diameter piping in, or you can add a lot of valves to try to control the flow everywhere in the system. And if you put too many valves in, that pressure, you have to pay for that pressure drop in pumping power. Okay, so the other traditional design guidance, actually, this comes up to the next slide. I had meant to delete that. There. Right, is the guidance, this just goes back right to the, I think to the late 1970s, earlier work done at Oklahoma State University, was that the flow should be turbulent inside the U-tube. That would be a bare minimum Reynolds number 2300, but probably 3000 or higher to make sure you actually have turbulent flow. And that's workable for cooling dominated systems, which are for the most part what we have here in Oklahoma. It can be problematic for heating dominated systems where you're using antifreeze mixtures, and what you'll find is that if you have to have a fairly high concentration of either ethyl alcohol or propylene glycol, the increase in viscosity as you get to low temperatures means it gets harder and harder to always have turbulent flow. You can, if you say under absolute worst conditions I have to have turbulent flow, you'll often find that you need quite high velocities. So, and then at that point, these high velocities, that you have to pay for those also. So yeah, actually, in the previous slide, right, I mentioned that ways to do this include small diameter pipes. Ways to exceed this and make a bad system include valves and small diameter pipes in the U-tube and so on. I should have said it also includes oversizing your pump, right? So that you end up with too high a flow rate. And when we go out and measure system performance, we see a lot of systems where there's very small delta T's across the ground heat exchanger. In other words, we have very high flow rate, and of course that leads to a lot of excess pumping power. So, but on this, I would say this issue of exactly what to do for heating dominated systems, I don't think it's completely resolved. You might look at our paper, which is also available on our website, where we look at some of the trade-offs for a specific system design. And I think probably for systems in cold climates or heating dominated, we have to allow laminar flow at the lowest temperatures. Okay, also there's a fluid factor, which you just put in as a number between 1 and 2, probably would be typical values. We added this some years ago. What it does is it accounts for the effect of the fluid outside the ground heat exchanger. So in the rest of the system, you have a certain amount of fluid, a certain amount of thermal mass. So when you have your peak load, especially if you have an hour peak load or 2-hour peak load, the effect of that fluid on the outside, it damps the temperature response. So I've done some calculations for some systems where when I do the calculation, looking at where the heat pumps are in the building, and we're talking about heat systems with distributed heat pumps, I found it wasn't unusual to have the same amount of fluid outside the borehole and the rest of the piping as you have inside the borehole. So if you double that, right, you'll decrease this peak temperature rise, particularly if it's short, right? And this, you have to look at the loads lecture, but sometimes you have a very short peak, sometimes you have a long peak, but particularly with a short peak, this extra damping can make a difference. So you can calculate it for your system, and you can add it back in. Okay, so we'll stop there and come back with part 2.